Now, let us go back and in the remaining time see what is the stress distribution, or how is the torque and the angle of twist related, and how is the maximum shear stress and torque related for this square cross section, thin wall square cross section. Okay. So, I am interested in finding the, let us assume the section has uniform thickness and mid dimension is A, this mid dimension is A and the thickness is T. Assume one uniform thickness T for the square shape cross section. Okay. And I am interested in finding one how is T and tau max relationship, the maximum shear stress and the torque relationship, and I am interested in finding the torque and angle of twist per unit length relationship. Okay. Now, for this the enclosed area, I have to use these expressions essentially. Now, the enclosed area for this cross section is would be this area. Would be this area, okay, which is A square, okay, which will be A square, because the area of the square cross section is center line dimension is what I gave it as A. So, there will be A square, okay. Then my torque is related as 2 times tau T A square, okay. Now, thickness is same in the cross section. So, tau max or the maximum shear stress or the uniform shear stress in the cross section would be T by 2 T A square, okay. Similarly, the angle of twist is now given by T by 4 mu A power 4, the line integral ds by T. T is uniform in this cross section, so I pull that out. So, this will be T by 4 mu A power 4 into T to line integral of ds. ds is the circumferential, this is nothing but the circumference of the cross section okay. So, that is nothing but for square, you know, the circumferential length is what is 4 A, okay, is 4 A, and hence omega would be related through as mu A cube T, okay. So, this is the relationship between tau max and the angle of twist per unit length. If the thickness were to change, then I have to integrate this line integral over each leg of the square with the different thickness, okay. So, that is what will change, okay. And similarly, if the thickness changes, tau max would be tau T is T by A square 2 A square, then tau max would be for the branch which has the least thickness will give me the maximum shear stress, okay. So, I have to use that fact that T is a function of S and tau is a function of S, and the branch that has the least thickness will give me the maximum shear stress, okay. So, with this we conclude our discussion on torsion. What we have seen is, we have seen how to analyze closed sections subjected to a twisting moment or torsional moment. that we saw in the last class. We derived a torsion equation T by J equal to tau by R equal to mu omega, okay. And then in today's class we saw what happens when there is warping. We did not go into detailed analysis of analyzing structures with warping, but we saw that for a rectangular section how you can generate a generic solution, and I presented the final result alone, and we used that to find the relationship between torque and the twist and the angle of twist per unit length, or torque and the maximum shear stress that this section will see. And then we went ahead and solved problems wherein we had thin wall sections, closed sections which will also warp, okay. It is not open sections, it is closed in the sense there is no discontinuity in the geometry, which will also warp. And how to analyze those structures? We saw that the torque is given by 2 times the shear stress times the thickness times the enclosed area of the cross section, and the angle of twist per unit length also we found it to be given by this expression in here, okay, to be given by that expression in there, okay. So, in the next class we will look at a different boundary value problem. Thank you.